Consider this rectangle. Now we could look at the angles in this rectangle. And we know that each of the 4 angles in a rectangle are 90-degree right angles. Given that fact, clearly we could work out what the 4 angles in a rectangle add up to. That the total of the 4 angles inside any rectangle will be 90 plus 90 plus 90 plus 90 is 360 degrees. Nothing particularly surprising about that, given that we already knew the size of the angles in a rectangle. But is there another way that we can prove this fact? Well, yes, there is. And we could go back to one of those angle properties that we've already found, one of those angle rules. And I could do this with my rectangle. I could draw in one of those diagonals. I could have done the other diagonal as well, but I've gone for this one. Now that I've done that, what have I got? Well, I have got one triangle here, which I'm going to label with a 1, and I've got one triangle here, which I'm going to label with a 2. Why is that a useful thing to do? Well, let's just fill in the angles of each triangle. So now that we've marked the angles of the triangles on there, we've got the green triangle 1 at the top and the purple triangle 2 at the bottom. And let's look closely at the angles in those triangles. So the top left angle of the rectangle is taken care of by the green triangle's first angle. This bottom right corner here is taken care of by the purple triangle's first angle. The other 2 corners of the rectangle are made up of one green and one purple angle. All 3 angles of the purple triangle and all 3 angles of the green triangle are part of the angles of the rectangle. There are no extra angles that have suddenly appeared, and the angles of the triangles cover all the angles of the rectangle. Therefore, the 3 angles in the purple triangle added to the 3 angles in the green triangle will give us the angles inside the rectangle. What do the angles inside the purple triangle add up to? And what do the angles inside the green triangle add up to? Well, they're both triangles, so they are both 180 degrees. So that's 180 degrees from the green triangle and 180 degrees from the purple triangle. And because the 3 angles in each triangle cover all of the angles in the original rectangle and nothing extra, we can simply add those 2 numbers together. 180 plus 180 is 360 degrees. And once again, we've proved what we already knew, that the angles in that rectangle add up to 360 degrees. But why would we bother doing this when we could just do what we did first? And look at the 4 right angles we've got inside this rectangle, 90 degrees each, add them together. Well, let's have a think. Let's have a look at another 4-sided shape. Here we have a parallelogram. Now we have no idea what the angles inside that parallelogram are. There are 4 of them, clearly, because it's a 4-sided shape, but we don't know what any of them are, so we can't add them up to see if they add up to anything interesting. But surely we could split this shape into 2 triangles. We could have the first triangle up here, number 1, and we cover 1, 2, 3 green angles, and we could have a purple triangle, number 2, and we could cover 1, 2, 3 angles. The 3 green angles and the 3 purple angles together cover all 4 angles of the parallelogram, and they don't cover anything extra. So surely, once again, we've got exactly what we had here, and we have got that the total angles inside the parallelogram are 180 degrees from the green triangle, plus 180 degrees from the purple triangle, added together to give us 360 degrees in total. And now that's two four-sided shapes, two different four-sided shapes that we've found have inside angles that add up to 360 degrees. And that seems like it might be an interesting thing. Let's test a couple more shapes. 4 more quadrilaterals, 4 more four-sided shapes. And the question is, can we do the same thing and join two corners to split these shapes into triangles? Well, surely for this kite we could go, for example, top to bottom. We could also go left to right and split it into just two triangles there. Why only two? Well, we could split this into as many triangles as we wanted, but we're only going to do two because the angles in these two triangles together will cover all of the angles in the original shape and nothing more. And that's the key thing, the and nothing more. We can't end up inventing extra angles. But here again, 180 in green, 180 in purple, 360 degrees. This trapezium then, we could go those two corners joined. 3 angles in green, 180, and 3 angles in purple, 180 again. And again, we've not gained any new angles. We've split these two angles in two, but we've not gained any extra angles in the original shape. And this final one, this is an irregular quadrilateral because it's not one of the recognised ones, and the sides are not all the same name. In fact, it's not particularly a named thing. It looks a little bit like an arrowhead. But we could go here to split into two triangles. And when we fill in the angles in green and in purple, then we find that we have covered all 4 angles in the original shape. That's 1, 2, 3 and 4 here, this reflex one, and we've not gained any extra information. The 5 examples there should be enough to convince us that this is going to work every time. So we can draw out another angle rule. And the angle rule that we can draw out is that angles in a quadrilateral, that's a 4-sided shape, will always add to 360 degrees. And if we're using this fact, if we are looking at a quadrilateral and we're using this fact to find a missing one, say, if we were given 3, for example, and asked to find a 4th angle, we could use the fact that angles in a quadrilateral add to 360 degrees, and we can quote that. But the question is, having found facts about the inside angles of triangles, adding up to 180 degrees, and of quadrilaterals, adding up to 360 degrees, the question is, are there similar facts and similar properties, maybe even similar rules, that we could find for bigger shapes? For some of those other polygons that we looked at, things like the Pentagon or the Hexagon, and so on. Well, let's investigate this further, but before we do, we need another piece of terminology, a particular name for something. The angles inside a shape of any size, any shape that we happen to be looking at, the angles inside a shape are called interior angles. Which kind of makes sense because interior is another word for inside. Another thing to notice is that the triangle in the top left has 3 interior angles, the rectangle has 4, this arrowhead at the bottom has 4, and the pentagon has 5. There is a connection between the number of interior angles and the number of sides that a shape has. A shape will have the same number of interior angles and sides. So let's test some of this out by looking at the next shape up, the pentagon. So we have a picture of a pentagon. We know it's a pentagon because it's got 1, 2, 3, 4, 5 sides. If it's got 5 sides, that means it must also have 5 angles inside it, 5 interior angles. And we're going to have a look at splitting this shape up in much the same way that we did with the 4-sided shapes, the quadrilaterals. And we'll see if anything interesting comes out of this. This is a process that you might have to go through for an exam question. You might have to show that you can work out certain facts about the interior angles in a shape. So you could get this exact question. We've broken it down a bit more here into stages, but you could get this exact question. Well, first thing we need to notice, this is a regular pentagon. What do we mean when we say the shape is regular? Well, regular means it's got the same length sides and the angles are all the same size. We can find facts about the interior angles of any pentagon, whether it's regular or not, but the whole of this process, the whole of this fact finding we're going to do, will only work with regular pentagons. First thing we need to work out the sum, the total of the interior angles. Well, it's got 5 of them, and we've no idea what they are. But we could do that splitting it up into triangles thing again. Now we have to be careful that when we're splitting this up into triangles, we don't add any extra angles in. So what I'm going to do, I'm going to do this in a very systematic, very careful way. I'm not just going to draw lines all over the place. I'm going to instead choose a corner. Doesn't matter which corner I choose, but I'm going to choose a corner. I'm going to pick this one. And I am now going to, with a ruler, draw a line from this corner to each of the other 4 corners in turn. And after I've drawn a line, I'm going to return to my chosen corner and draw in the next line. So I'm going to first of all join this corner to this top one. Well, it's already joined by this side, so that's okay. Don't need to do anything there. I'm then going to come back to my chosen corner and I'm going to draw a line between there and this one over here. And then I'm going to return to my chosen corner and I'm going to draw a line between here and this bottom right corner here. And then I'm going to return to my chosen corner and I'm going to draw a line between my chosen corner and this bottom left one here. It's already drawn in. It's the side. I've joined up all of the other corners. I now have 1, 2, 3 triangles. I have triangle 1 in green, and I could mark on the 3 angles of triangle 1. I have triangle 2 in the middle, in blue, and I could mark on the angles of triangle 2. And I also have triangle 3 in red at the bottom. And I could mark those angles on as well. If I do that, and then look at what I've got, well, think about the 5 angles inside the pentagon. 1, that's covered by this green one. This one here, that's 2, is covered by the green and the blue. This one here, covered by the blue and the red. This one here, covered by just the red. This one here, covered by all 3. 1 green, 1 red, 1 blue. There are no extra green, red or blue angles marked in this pentagon, so we have managed to cover all of the original angles in the pentagon and nothing else. So what have we got? Well, we've got 180 degrees from the green, 180 degrees from the blue, and 180 degrees from the red. So surely what we've got then, to work out the total, is we've got 3 lots of 180 degrees. And 3 times 180 degrees (540 degrees). So the sum, the total of the interior angles in any pentagon will be 540 degrees. You do not need to know that as a fact. But you do need to know how to find that information like we've just done. The next question asks us for the size of one interior angle. Well, this is the clever bit, and this is why this only works for a regular pentagon in this case. We know that those 5 angles add up to 540 degrees. We've just found that. And we also know something else about the 5 angles. We know that they are all the same size. How do we know? We know that they're all the same size because this is a regular pentagon. And in a regular pentagon, the 5 angles will be the same size. If they are the same size, then surely we could just take the 540 degrees and we could share it out, divide it among the 5 angles, 540 divided by 5, and that will give us the size of one angle, being 108 degrees. And looking at that angle, that feels like it could be 108 degrees. Now the next question asks us to find the size of one exterior angle. Now we haven't got any idea what exterior angles are. But presumably, if we have an interior angle, it kind of makes sense that we would have an exterior angle. Because why would we call something an interior and not then have a matching exterior? So all we really need to do is just draw on what turn out to be the exterior angles. Now exterior angles are defined in a very particular way. So what we're going to do is we are going to get a ruler and we are going to extend each of the sides a little bit, but in the same direction each time. So I'm going to extend towards the left. It doesn't really matter which one we do, but I'm going to extend towards the left, and I'm going to extend this side towards the left like that. And then I'm going to extend this side towards the left in the same way. I'm going to extend it in the same way. And then I'm going to extend this side in the same way. And then I'm going to extend this side in the same way. And then I'm going to extend this side in the same way. And then I'm going to mark on some angles. And the angles I've marked on in pink are the exterior angles. Why? Because that's just what was chosen to give the name exterior angles to. The angle was chosen and then a name was applied to it. Now we're not going to measure these angles, we're going to use what we already know. First thing to notice, how many exterior angles does this shape have? Well, it has 1, 2, 3, 4, 5, which should come as no surprise. If the shape has 5 interior angles, it kind of makes sense that it would have 5 exterior angles as well. And notice that each exterior angle is paired up with an interior angle. If we look at this one down here that we've labelled, for example, we can see the interior angle here, just this red bit, pairing up with this exterior angle here. If the interior angles are all the same size, then the exterior angles will also all be the same size as each other. But they will not be the same size as the interior. How are we going to work out the size of the exterior angle? Well, we're going to really focus in on this bit down here. Because here is an exterior angle and an interior angle. What is true about the interior and exterior angles of this shape? Well, look at the two things together. They are sitting at a point on a straight line, the bottom edge of that shape. The two angles together, the interior and the exterior, make a half turn, or 180 degrees. So surely the exterior angle would be 180 degrees, take away whatever the size of this angle here is. And this angle here we know is an interior angle. And we've just found that the interior angles are 180 degrees. So the exterior will be 180 degrees less the 108. This is 108, remember, because it's an interior angle. So it'll be 180 degrees less the 108 comes to 72 degrees. And again, that is not something you are expected to know, but you do need to be able to follow this process. And the final thing we are asked for is we are asked to write down the sum, the total, of the exterior angles. Well, we've just said that it has 1, 2, 3, 4, 5 exterior angles. We've just found the size of one of them. One of them is 72 degrees. So let's say that the sum will be 5 lots of 72 degrees, and that comes to 360 degrees. Now this process for finding, say, the sum of the interior angles, the size of one of the interior angles, the size of one exterior, the sum of the exterior angles, you might have to do this for any shape at all. So we'll do another one, and we'll do it a little bit quicker. And then we'll start to look at the results we've got from the triangle, the quadrilateral, the pentagon, and this next shape, and we'll see if there are any other patterns that we can spot. So let's have a look at another one of these shapes. So we've got a hexagon this time, and we're going to go through exactly the same process again. Once again, this is a regular hexagon. When we say it is regular, we mean that the sides are the same length, and the angles are the same size. As in the interior angles. We need to find the total of the interior angles. So I'm going to pick a corner, I'm going to pick this corner, and I'm going to draw a line, a straight line with a ruler from this corner to each of the other corners in turn, fanning out from that point. Here to here is already done. So we can go to this next corner then, we can draw this line in like that. And then we can go from this original point again, and we can draw one straight across the shape. And then we can draw this one in as well. There it is. And then this last one is already drawn in. It's along the side length. There we go. If we were to fill in the angles of the triangles, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, we can see that we have covered all the angles in the original shape and nothing extra. We have got 1, 2, 3, 4 triangles there. So the total will be 4 lots of 180 degrees because the angles in any triangle add to 180. 4 lots of the 180 comes to 720 degrees. We want to find the size of one interior angle. Well, the number of interior angles and the number of sides the shape has are the same. We know that the angles inside the hexagon add up to 720 degrees. It's a hexagon, it's got 6 sides, so there must be 6 angles. So the size of one of them, they're all the same, remember, because it's regular. 720 divided by 6 is 120 degrees. And looking at that shape, that feels like it could be 120 degrees, this angle here, say. Now I'm going to mark that on as being 120 degrees. Why? Because I'm next asked to find the size of one exterior angle. Well, to find the exterior angle, I'm going to fan out for each of these sides. I'm going to do it in the other direction this time just to prove that it still counts, it still works in the same way. But we're always fanning out a little bit like, sort of like a Catherine wheel, if you like. So just going to extend those sides in the same direction each time. These lines should never cross. We're only ever extending the side in one direction, in the same direction. And there we go. We can mark on the exterior angles. There, 3, 4, 5 and 6. 6 interior, 6 exterior. Let's look at this pair down here where I've labelled the 120 degrees. The exterior angle then must be angles at a point on a straight line add to 180 degrees. So the 120 and this exterior angle must add to 180 degrees. The interior is 120, so the exterior will be 180 less the 120s to give us 60 degrees for each of those exterior angles. And the final thing, we're asked for the sum of the exterior angles. Well, there are 6 interior and 6 exterior. So if we were to add 6 copies of the 60 degrees together, or rather have 6 lots of 60, 6 times 60 degrees, comes to 360 degrees for the total of the exterior angles there.
So the first thing we can draw out of this is this fact that one interior angle plus one exterior angle will add to 180 degrees, like we've just seen with the pentagon and with the hexagon. In fact, we used that very property to find the size of the exterior angle. The only reason for this property to exist is because this is how it was set up. It was defined that an exterior angle and an interior angle would work together in this way, and that's how an exterior angle was settled on. But it is worth bearing in mind, because that as a fact will help us with this next thing. So what we're going to do is we're going to start to collate some of the information we've got from various different places about interior and exterior angles, and we can see if we can spot anything interesting going on. So we're going to fill in a table. Now this table comes with a warning. You absolutely do not need to remember or learn anything in this table besides the things we've already talked about. Well, let's see what information we're going to put in this table. So we have got the names of some shapes and the sides, the number of sides that they have listed as well. So we've got triangles, quadrilaterals, 4-sided shapes, the pentagon and hexagon we've just looked at, and then a 7-sided heptagon, an 8-sided octagon, a 9-sided nonagon, and a 10-sided decagon. We need to fill in the information for the total interior angles, the size of one interior angle, the size of one exterior angle, and the sum of the exterior angles. Exactly what we've just been looking at for the pentagon and the hexagon. So let's put those in. Let's put in the information for the pentagon there and the information for the hexagon there. Now, we also know some of these facts about triangles and quadrilaterals, so we should be able to fill those in as well. If we look at the triangle, say, we already know that the interior angles in a triangle add to 180 degrees. The angles inside any triangle will add to 180 degrees. And we can also find the size of one interior angle. We're talking about regular shapes here for all of this. And if we're thinking about regular shapes, a regular triangle is one in which all the sides are the same, all the angles are the same. That's an equilateral triangle. And we know the angles in an equilateral triangle are each 60 degrees. 180 divided across the 3 give us 60 degrees. From that, we should then be able to find the size of an exterior angle. As we've just said that one interior plus one exterior add up to 180 degrees. So if the interior is 60, the exterior must be whatever else we need to get up to the 180. So it will be 120 degrees. And if a triangle has 3 sides, 3 interior angles, that means it also must have 3 exterior angles. So the sum of the exterior angles will be 3 lots of 120, comes to 360 degrees. And maybe we're starting to spot something interesting going on, but let's keep going. We can fill in some of this information for a quadrilateral. We know from earlier on the angles inside a 4-sided shape, a quadrilateral, add to 360 degrees. That was one of our angle properties. If there are 4 of them, we can share the 360 degrees across the 4 angles. We get 90 degrees each. Well, that makes sense because a regular quadrilateral, a regular 4-sided shape, is a square, and the angles inside a square are 90-degree right angles. If the interior angle is 90 degrees, the interior and the exterior add to 180, so the exterior must also be 90 degrees. And if there are 4 of them, 4 sides, 4 interior angles, so 4 exterior angles, 4 lots of 90, also 360 degrees. Now, we could go through the same process that we went through with the Pentagon and the Hexagon for the heptagon, octagon, nonagon, decagon. And if we did, then we would get these numbers for the heptagon, these for the octagon, these for the nonagon, and these for the decagon. You could easily check them yourself. If you wanted, you could just draw yourself one of these shapes and have a go at exactly the same process and prove to yourself that these are the numbers that come out. First thing it's worth noticing, just before we spot the very obvious pattern, but first thing that's worth noticing, the total of the interior angles gets bigger each time. Well, that makes sense because we've got more of them. The size of the interior angle also gets bigger. Well, think about it. If there are more angles and there are more sides, the shape kind of spreads out a little bit. So the interior angle gets bigger and opens out. And if the interior angle is getting bigger, then the exterior angle has to get smaller. A final reminder on the information in this table before we spot the really obvious pattern. Again, don't learn these. There is one fact that we're going to draw out of this, and a couple of ideas, I guess. Apart from the angles in a triangle adding up to 180 degrees, the angles in a quadrilateral adding up to 360, and the process that we went through for the pentagon and the hexagon, that's as much as we need. But you do need to know how to do that process. Because you could be given a pentagon, a hexagon, a heptagon, an octagon, a nonagon, or a decagon in an exam question and asked to do some or all of that process that we did. Right, we've ignored the elephant in the room for far too long. What is the really obvious thing it's worth noticing in this table? I would say it's this column here. The sum of the exterior angles for those different shapes is always, here at least, 360 degrees. And it turns out that that is always the case. And this can be another of our angle rules, angle properties. The exterior angles in any polygon, any shape, effectively, will add to 360 degrees. And there is actually a very good reason for that. If we look at the polygons we've been talking about from pentagon through hexagon, heptagon, octagon, nonagon, decagon, and really look at what's happening as we add more sides and more angles, we should be able to work out why the angles, the exterior angles, always add to 360 degrees. What happens to the look of the polygon as we add more sides. And then try and picture what would happen if we added even more. If we went to say 20 sides or 50 sides or 100 sides or 1,000 sides, the interior angle would shallow out even more and the sides would get smaller and smaller. And it would start to look increasingly like a circle. And the angles in a circle, effectively a full turn, 360 degrees. And in fact, this very thought is the basis of one of the oldest debates in maths. Some mathematicians will argue that a circle is one single-sided shape where the side starts and ends at the same point and there are no angles in it. Whereas some mathematicians will argue that a circle is a shape that has infinitely many, infinitely small sides that are so infinitely small that we can't see them as separate sides and can only perceive them as one continuous loop. And some people would argue that it doesn't really matter either way, and it's just a fact that the exterior angles in any polygon add to 360 degrees. Bang, done.